Everyone, and welcome to this video. This video is our second lesson on matrices for A-level, where we will be covering the inverse matrix and the determinants of matrices. Let's get started. What is a determinant? It is a scalar quantity that gives us information about the matrix that we have. In this way, it is like the modulus of a vector, and it has a particular significance which we will be covering in a later lesson, which is usually in transformations. It is worth noting that only square matrices have determinants, and you will only need to specifically learn how to calculate this for 2x2 matrices and 3x3 matrices at A level. It is often written shortly as what is seen on the screen. Let's learn how to calculate it for a 2x2 matrix. For a 2x2 matrix, the evaluation of the determinant is as follows. First, we must find the product of the elements in the leading diagonal, which we covered in an earlier lesson. Then we must find the product of the elements in the counter diagonal, which is the diagonal opposite to the leading diagonal. Then we must subtract the value for the counter diagonal from the value for the leading diagonal. Let's show this algebraically. We will do it here with matrix A. And by undergoing this process, we see that for matrix A, the determinant is AD minus BC. Let's now do this for a matrix with numerical values. By undergoing the exact same process, we see that the determinant for B is 5. Let's now cover some rules about determinants for both 2x2 matrices and general square matrices. The first rule, written in yellow, applies for all square matrices, and the second rule, written in blue, applies for only 2x2 matrices. Let's now learn how to calculate the determinant for a 3x3 matrix. For a 3x3 matrix, the evaluation of the determinant is as follows. We will define a general 3x3 matrix, and we will write the formula for the determinant of A below. Now you may wonder how this is formed. Well, the visual next may help to understand this. As you can see, the coefficients of each of the determinant lines, or the submatrices, are all in the top row of the 3x3 matrix. You may also notice that there are alternating signs between each of these top three elements. So A is positive, B is negative, and C is positive. Now, how are these submatrices formed? Well, they are formed by selecting the top relevant element for each element of the top row, and then deleting their respective row and column. So for A, we will delete the row that it's in, and we will delete the column that it's in. This would leave us with E, F, H, and I, which you will realize is the four values which are in the submatrix right next to the A. Note that the single lines that are surrounding these submatrices denote that we must calculate the determinant for these 2x2 submatrices. You will then see this with B. The ones that aren't in any row or column of B are D, F, G, and I, and same with C. D, E, G, and H are the ones which are not in the same row and column as it. Now let's cover what an inverse matrix is. The inverse matrix is a matrix that, when multiplied by the original matrix, will result in the identity produced. Using the inverse, we can solve the matrix equations. It is denoted using the notation seen on the screen. And if we had an equation such as CZ equals D as seen on the screen, and we had the matrices C and D, using the inverse, we can find the matrix Z by using the inverse of C. Let's see how we will do this. So we must use the inverse property which we covered in the earlier video. And if we consider our original equation and multiply both sides by the inverse of C, we can see that the first two matrices will combine to make the identity. And the identity multiplied by Z will simply form Z, as again we covered in the earlier video. And this would mean that Z would be equal to the inverse of C multiplied by D. And in this order specifically, because as you may remember from the earlier video, matrix multiplication matters in which order it comes in. Now let's cover inverse of 2 by 2 matrices. We can use this to help solve equations like we saw previously. To form the inverse of a 2 by 2 matrix, we swap the positions of the elements on the leading diagonal and multiply the elements on the counter diagonal by -1. And then with this new matrix that we have formed, we multiply it by the reciprocal of the determinant of the original matrix, so 1 over the determinant of the matrix. So if we do this with a general matrix, A, as we defined earlier, we can then form its inverse. Now let's cover the inverse of 3 by 3 matrices, which is slightly more difficult, but with a bit of explanation it should be relatively understandable. Here we have a numerical matrix of A. And first we must form a matrix of cofactors. Now how do we form this matrix of cofactors? Let's select the first element, 3. As you can see, there is a sign pattern on the right hand side. This is important because it refers to the sign in front of each matrix, each cofactor in the matrix of cofactors. So for 3, we must undergo a process a bit like how we did for the determinant of 3 by 3 matrices. So for 3, we must delete the row and column that it is in, and then the remaining elements that are not in the same row and or column as 3 are the ones which form the cofactor within this matrix of cofactor in that relevant position. So you may realize that the matrix of cofactor is of the same dimensions as the original 3 by 3 matrix, because we must have a cofactor for each respective element. So obviously for 3 we delete its row and its column, and we see that 9, -7, 0 and -4 are the elements that are left over, and this forms a cofactor. And of course we must take the determinant of this, and you saw that notation earlier on in the video. And note that these cofactors must be multiplied, or at least given, the sign that is in the sign pattern. And you may realize that the sign pattern is just alternating, so it shouldn't be difficult to remember. And we can do this for all elements. So as you can see in the green, we are selecting the elements which aren't in the same row or column as the position in the matrix of cofactors. Now that we have formed our matrix of cofactors, we can evaluate the values inside this cofactor matrix and get the matrix C. Now we must transpose this matrix C. This is part of the process for getting the inverse matrix of A. And we've done the transpose as we covered in an earlier video. And here is A, just as a reminder. We must now evaluate the determinant of A, which has been done at the bottom of the screen. And we can use this formula shown on the screen to form the final inverse matrix for A. So now let's cover some special instances. Some matrices that are square do not have an inverse. These matrices are referred to as singular matrices. Matrices are singular if their determinant is 0 and this applies for all dimensions of square matrix. Now, let's consider some uses of the inverse matrix. How would we find the inverse matrix of the product of matrices in terms of the individual matrices themselves? Let's define some matrices, A, B, and C. Here is the formula for the inverse of the multiplied. But how do we prove this formula? Given that A, B, and C are non-singular, we can prove that the determinant of their product is also non-singular, using the rule that we covered in the earlier part of the video. And we can then prove this formula algebraically. This is done by multiplying the formula seen on the screen gradually by the inverse of A, the inverse of B, and then the inverse of C. And as you may realize, we just are using the associative property, which we covered in an earlier video, to derive this formula. The formula on the bottom, this AB inverse is equal to the B inverse times by the A inverse, comes from the same proof as the formula above. However, it is a little shorter, and if you want, you can cover it in your own time. But using the same logic as the proof that we just saw, we can derive this formula. Thank you very much for watching. Feel free to leave any questions in the comments and I will be happy to answer. And I hope to see you in the next video.